AC voltage applied to an inductor. An AC source connected to an inductor in the figure given below. Usually, inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance. Thus, the circuit is a purely inductive AC circuit. Let the voltage across the source be nu equals to nu m sin omega t. Using Kirchhoff's loop rule, which says that summation of EMF as function of t equals 0, and moreover, since there is no resistor in the circuit, we have V minus LdI by dt equals to 0. Inductance is an effect which results from the magnetic field that forms around a current carrying conductor. Change in current creates a magnetic flux that generates an electromotive force. Inductance is a measure of this generated EMF. For example, an inductor with an inductance of 1 Henry produces an EMF of 1 volt. When the current through the inductor changes at the rate of 1 ampere per second. Minus LdI by dt equals to EL is the self-induced EMF in the inductor. EMF is induced in a single isolated coil due to change of flux through the coil by means of varying the current through the same coil. This phenomenon is called self-induction. We know for an inductor N phi B equals L into I. Now according to Faraday's second law, EL equals minus d by dt of N into phi B, that is equal to d by dt of L into I. Therefore, induced EMF is minus LdI by dt. Current as a function of time. If nu minus LdI by dt equals 0, then di can be written as di equals nu m by L into sin omega t. Now on integrating both sides, we get I equals minus nu m by omega I into cos omega t plus constant. Now as constant is 0 and minus cos omega t can be written as sin omega t minus pi by 2. So we can write I as Im into sin omega t minus pi by 2. Phasor diagram. On the left hand side, you can see the graph of voltage and current versus omega t, and on the right hand side, a phasor diagram for the circuit is shown. Click on the play button. The source voltage and the current in an inductor shows that the current lags the voltage by pi by 2 or 1/4 cycle. The current phasor I is pi by 2 behind the voltage phasor. The current reaches its maximum value later than the voltage by 1/4 of a period. Therefore, T by 4 equals pi by 2 by omega. We have seen that an inductor has reactance that limits current, similar to resistance in a DC circuit. Does it also consume power like a resistance? Let us try to find out. Power is the product of current and electric potential. That is equal to Im sin omega t minus pi by 2 into nu m sin omega t. Now writing sin omega t minus pi by 2 as minus cos omega t and then multiplying and dividing the equation by 2, we get minus Im nu m by 2 into sin 2 omega t. Now as we know, the average of sin 2 omega t over a complete cycle is 0. So finally we get the average power over a complete cycle is 0. Let's take an example. A pure inductor of 25.0 millihenry is connected to a source of 220 volts. Find the inductive reactance and RMS current in the circuit if the frequency of the source is 50 Hz. Solution. The inductive reactance XL is 2 pi nu L. Putting the given values in the equation, we get the result as 7.85 ohm. The RMS current in the circuit is V by XL, which gives the result 28 amperes.